start recording.
Okay, glad you asked that question. Okay. Yeah. So, yes, when we're talking about hyperbolic geometry, you're talking about this field of mathematics. We need functions to work with. Okay, and we do have functions to work with, which are quite some fun ones, I like to think. And let me introduce them to you. Okay, so this is the hyperbolic sign. It looks like sine, except there's an H now. Okay. Now, this actually has a definition to it that makes it a little more grounded. Like we can, we don't just have to be like plug it in and memorize values, but I can more easily use other functions to describe it. In this case, the hyperbolic sign is equal to e to the x minus e to the minus x over 2. Okay. Hyperbolic cosine is equal to e to the x plus e to the minus x. So this is the hyperbolic sign, this is the hyperbolic cosine. You may be first asking yourself, like, why? Why in the world would I want to care about these at all? And the reason is actually something very interesting. I might go ahead and point this out. So we've all seen bridges, right? Maybe I'll try to draw a quick example, right? Where you have like kind of the wire that's going between them and form this curve, right? Now, many of you looking at that, actually, I mean, you've seen a bridge like this, but let's even just talk about the St. Louis Arch. Right? A lot of you may look at these things and say, oh, well, that's kind of making a parabola shape. This looks like a parabola. You're actually wrong. Both of these are the hyperbolic cosine. So the natural shape of a wire between on a bridge is actually the hyperbolic cosine function. So this is actually very useful to describe the behavior of real life objects, unlike what it may seem. And it's just a combination of E function, which is sort of funny. So I'll go ahead and do these pictures, but just as a fun fact. So if you're on a bridge and one of your friends says, wow, look at that parabola shape, you can just say, you're wrong. That's not a parabola. That's hyperbolic cosine. So, okay, from here, you could write every other like function in terms of this e to the x form, but we can just kind of represent everything else in terms of sinh and cosh. So tangent is the same thing as sinh x over cosh x. Secant, the 1 over cosh. Cosec, sinh, usually I hear it as tangent, but there's no C. It's not ranch. Okay, so these are the hyperbolic functions. And the book kind of shows the graph of them. I've already demonstrated kind of what cosh looks like, but I'll draw it again. So if you plug in 0 into cosh, I'm going to get e to the 0, which is what? 1 plus e to the 0 again, which is 1, so you get 2 over 2. So it actually starts at 1, and then like I said, it's gonna add up both sides, so it makes this short shape. Okay, and this kind of makes sense. The book demonstrates a little bit. Maybe I'll go ahead and do that as well. That does make sense in terms of like if I just look at, so this is, we'll say this is 1/2 e to the x, which, well, if it's 1/2 e to the x, it should be a little bit. So, and 1/2 e to the negative x, right? Which we talked about, a base to the x, like if it's greater than 1, it's going to go this way, and we talked about one's less than 1, but we didn't really do negative as much. But remember, e to the negative x is the same thing as 1 over e to the x, which is 1 over e and then to the x power, right? Because 1 is the same as 1 to the x is still 1. So this kind of puts it in a format we're more familiar with. So it's going to look something. So if we add these up, we get that. Okay. Sinh, maybe I'll do that in orange. Looks like. So I'm subtracting these two curves in a way instead. Which this one, we were having this discussion about why tangent x cubed looks similar. Well, I would argue that sinh in x cubed look even more similar. So in terms of the curvature, so that's sinh, and then hyperbolic tangent, right? Really, it doesn't do as you would expect it to, where it goes up, because the sinh and the cosh are actually like pretty similar in terms of their values, aside from like right here, and it's just going to be positive or negative. And so that graph looks something. Okay, which is bounded between so that's kind of what those graphs look like. I'm not going to be too hard on like you got to remember what all those graphs look like, but just to give you a general idea and kind of how those are built off of each other. Okay, so we need some facts about our hyperbolic functions. So we're going to look at some hyperbolic identities. Okay. So as it looks right there, right, the orange curve is sinh, and sinh x, right, if I took it 180 degrees and I flipped it, it's still the same graph. So that means it's an odd function. Specifically, sinh of negative x is negative sinh x. Cosh, right, is the white graph here, is an even function, right? Because if I just flip it over the y-axis, it's going to land on itself. So that means cosh of negative x, cosh of x. Okay, you could also get that from just plugging in negative x in there and see what happens with the e functions. Let's see. Okay, now this one's interesting. Cosh squared x, sinh squared x. Oh, my bad. I'm sorry. I said that. I just wrote it. I said, do as I say, not as I do. Well, actually, do as I do. Just not in that case. Okay, cosh x, just positive coaches. Okay, cosh squared, sinh squared is 1. What goes in between? Right. Nope, it's a minus. Cosh squared x minus sinh squared x is 1. Wow. Pretty, it's a little different, right? We have a similar formula, but it's going to be set up a bit different. And maybe, because the book does it, I'll show you real quick what that is. So, cosh squared x minus sinh squared x. Cosh is the same thing as e to the x plus e to the negative x divided by 2, or squaring that, and then sinh is e to the x minus e to the negative x divided by 2. Okay. What is e to the x plus e to the negative x squared? How do I do that? Right, we need to FOIL it, right? Or, I mean, if you remember how to do reverse square, that's fine. FOIL that out. If I FOIL this, what am I going to get? What's the first term? What? What's e to the x times e to the x? E to the 2x, right? And that comes from, right, e to the x, e to the x. You can add the exponents together, so we get e to the 2x. Okay, what is e to the x times e to the negative x? Yep, they have, you just add the exponents, you get 0, which is going to be 1. What is, okay, we do the same in the middle, it's going to be plus 1. What is e to the negative x times e to the negative x? E to the negative 2x. Okay, but 1 plus 1 is 2. So here we're going to get e to the 2x plus 2 plus e to the negative 2x over 2 squared, which is going to be 4. Similarly, if we do this one, we're going to get e to the 2x. I'll write the minus here. And then we're going to get, right, instead of pluses now, we're going to have minus 1, which gives us minus 2, plus e to the negative 2x. And that's all going to be over 4. Okay. And then we can distribute this negative to the top. So we're going to get e to the 2x plus 2 plus e to the negative 2x minus e to the 2x plus 2 minus e to the negative 2. Okay. What's going to happen to all the e's? They all cancel. E to the 2x, e to the 2x, e to the negative 2x, negative 2x, 2 plus 2, it's 4, 4 over 4. Good. So that works out. Okay, so if you want to check any of these identities, you can just use the definitions there. Okay. Similarly, we have 1 minus tangent, hyperbolic tangent squared is it's positive secant squared. Okay. Again, I kind of showed earlier, but if you just divide cosh squared from all this, you get this. Okay. Finally, we have sinh of x plus y equals sinh x cosh y plus cosh x sinh y. Okay. And we have that cosh equals cosh x cosh y sinh x sinh y. And actually, these ones are the same. Right? Remember, when you're doing cosine of x plus y, you actually have to change the sign, but here we can keep it. Okay, so there's some identities of our hyperbolic functions. Okay, because obviously, if we have some good functions, we want to kind of study it a little bit, right? Okay, what we're going to find is, honestly, these functions are really easy to find the derivative of as well, because we already know how to do the derivative of e, right? So we'll just use our knowledge of the derivative of e to get the derivative of sinh. So let's do that. So I want to find the derivative of sinh x, which is going to be the derivative of e to the x minus e to the negative x over 2. Okay. Does anything happen with this 2? Nope. Why not? It's constant. So this is still going to be all over 2. The derivative of e to the x, e to the x. Okay. Minus, what's the derivative of e to the negative x? Good. You just multiply by a negative 1. Okay. But notice minus minus plus. What is that? This is the definition of hyperbolic cosine. So the derivative of sinh x is cosh x. Nice. Any guesses on what the derivative of cosh x is? Is it negative sinh x? Oh, it's actually just going to be positive sinh x. So that's going to be something to keep track of, okay? All right, let's close here. The derivative of cosh is sinh. So there's no negative sign happening here, right? So I can go between sinh and cos as many times as I want to. The derivative is always going to be positive. Derivative of cosh is sinh is cos is sinh is cos, back and forth, right? And then we also have just I didn't take much time on it. It's not as much as loss. Okay. Our other derivatives aren't bad either. Pretty much they're about as much as you expect them to be. Do it. So the derivative of tan is sec squared x. We have the derivative of hyperbolic cosecant is going to be negative cosecant x cotangent coth x. So those are as they typically are. Now the derivative of secant hyperbolic secant x actually also is a negative on it. So if you're done with hyperbolic secant, you actually have to put a negative sign on now. Whenever we did that derivative initially, you didn't have to worry about a negative sign, or like in terms of the trig function, you didn't have to worry about a negative, but now you do. And finally, negative. So your basic functions are all positive in the derivatives, and all the like extra ones that are 1 over them have negatives. Okay, so maybe an easy way to remember that. Okay. Good. Example time. So we are going to take the derivative of, and we'll just do sinh. No need to do anything too crazy. No, x squared plus 4. Okay. So this is, I guess, on this section.
When we take the derivative of
I meant to write squared. Thank you. Sorry to keep up this whole time. So, okay. Thank you. Yes, that is supposed to be squared. I apologize for that. So the derivative of sinh of x squared plus 4. So how do I do it? What's my first step?
the cos.
Fantastic. Yeah. So we do chain rule. I take the derivative of the outside part, which is cosh, right? Which is going to be cosh of x squared plus 4, and then I just multiply by the derivative of the inside, which is just 2. There you go. Yep.
Do we have to graph any of these on the final?
Like I said, you probably won't have to worry about it. It's good to know what they look like, but I've never had to like actually graph them. Just because the points, I mean, you can do like 0, but some of the other points are over. So, yep. Oh, you didn't. Okay. Gotcha. Cool. Well, there's that. Let's see. So that is the hyperbolic functions, right? But we're not done yet, right? Because we define these functions, and we want to define inverses of these functions too, right? So let's get some inverses. Okay, so we're going to have some inverse functions, which we'll define them as similar to how we did the inverse trig functions. like this. So I'm going to write just inverse sine inverse x, just -1. So this is the same statement as sinh of y x. We have cos inverse, thing as cos y equals x. Then we have tan inverse statement. Okay, so these are inverse functions. Okay, look just like the inverse triple ones, except now we just have an h in place of them. Okay, but just like here, we can actually get a solid. We can actually describe these differently than just saying sinh inverse and just kind of have it out in an abstract form. So I'm going to derive that here in a sec. But I figure, you know, let's we'll take some time here and we can kind of draw some the graphs of these, see what they look like. So sinh is pretty easy, right? Remember that the graph of sinh will look like this. Okay, so its inverse function, when I just flip it over, is going to look like okay. Okay, so this is y equals sinh. Okay, so there's no issue here because sinh is 1-to-1, right? It's just looks like x cubed in a way, right? It just keeps going up, always increasing. There's no problem. Okay, I've drawn cos a few times. Is that 1-to-1? No, absolutely not, because it looks like a parabola a little bit, but it's not. It doesn't have the same exact shape. So whenever we're going cos, which I'll do. This, we need to be careful, okay, because right now it's not 1-to-1, right? So similar to how they do a parabola, I'm just going to take one side of this, okay? And how that's important here is I need, whenever we're talking about cos, sinh and tans are fine, but y needs to be greater than 0 for the cos case, right? So I should only be having positive y values. I don't want to have any negative. And plug in negative y values in for the cos. It should be only a positive one. So its inverse graph is going to look something like this. Maybe kind of that general idea. Maybe it might be go a little higher. And then tangent, I'll do yellow. Tangent actually looks a little bit like. I'll just draw slightly different. The sine hyperbolic sine inverse, and so okay, so there you go. This is so you can have that if you kind of want an idea of those graphs. It's in the book as well, but you know, just have some fun between just to see what's going on. But we're going to take this thing and we're going to find its inverse. Okay. So if I give you a function, right, and I want you to find what the inverse function looks like, right? We had 3 steps, right? So the first day, what were we supposed to do? All right, what was the first step supposed to be? Right, we were, yeah, we need y equals f of x, which we have here. But specifically, if I want to get a different form than just sinh inverse, I want to use this one. So we have y equals e to the x minus e to the minus x over 2. Okay. What was our next step?
Solve it in terms of x.
Solve it in terms of x. Okay. So let's do that. So this is going to be a little bit of time, but let's go ahead and walk through it. Okay. So what is my first step in solving this for x? Let's not, so yeah, let's multiply by 2 first. It's possible that natural log is involved at some point, but it's going to be a while long, right? Because remember, I can only do a natural log if it's like things multiplying and I can expand it, right? But if I have a natural log of e to the x minus e to the minus x, I can't do anything with that. I have no idea what to do because they're subtracting, right? So we're gonna have to say that for the natural log for later. We'll use it. But I'm gonna multiply both sides by 2. And I'll definitely kind of help out from here. Because it's not super clear as to what the next step would be. But our ultimate goal, right, is to solve for x, right? So what we're going to do is instead of I'm not going to solve for x directly at the moment. I'm going to solve for e to the x. Okay. The way I'm going to do this, and maybe you'll see it once I bring everything over, is I'm going to have e to the x minus 2y minus e to the minus x equals 0. Okay. Which still isn't favorable to us. But what I'm going to do is I'm going to take both sides and I'm going to multiply it by e to the x. Okay, now let's think about why that is. What is e to the x times e to the x? What is e to the x times 2y? It's 2y e to the x. Is that it? And then what is e to the x times e to the minus x? Yes, it's going to be 1 because we're going to get x minus x, which is 0. So we get e to the 0, which is 1. Was it? We might be able to factor it. It is, although it's going to be kind of hard just because there's not really a clear, especially with this y here. So we're not going to factor it, but it's an interesting thing to notice to think about factoring it, right? Because we have 2x. We have e to the 2x, e to the x, and we have just a constant, right? But this e to the 2x I can even write as e to the x squared. So what kind of equation do I have? It's a quadratic. What formula do I have to solve quadratic equations? The quadratic formula. How about that? So we're going to have, so to solve this, I'm going to get e to the x equals, so we do negative b. What is b in this case? So it's going to be negative 2y, so we're going to get positive 2y plus or minus square root of 4y squared. Good. 4y squared. Okay. What's going to come next? So we're going to have minus 4, right, times minus 1 times 1. So we get plus 4. And this is going to be all over 2 because it's just 2 times. Good. Yeah, we can take a 4, factor it out. So I'm going to get 2, and even it's going to be a 2 that comes out, and I can factor it completely. So I'm going to get 2 times y plus or minus the square root of y squared plus 1. And then that's divided by 2. So I just simply get y plus or minus. Now, we do only need, so we have this as a right now, right? So if I want to solve this for x, what do? I have e to the x equals y plus or minus the square root of y squared plus 1. Take the natural log. So we're going to get x equals the natural log of, and we're going to have y plus or minus the square root. Okay. Can I keep both the plus and the minus? Is that valid? Is that okay? Good. So we can't take the natural log of something negative, right? So we better make sure we're not doing that. In the plus case, we're fine, right? Because you have y, which, well, actually, let's think about this, right? So if I have y, right, and I have the square root of y squared plus 1, which is bigger? Just barely, yep, because right, this is obviously y squared plus 1 is bigger than y squared, so but the square root of y squared is 1. So just a little bit. This is going to be bigger than this guy. So if I have a negative number plus a positive number that's bigger than it, we don't have a problem. So that's okay. However, if I do minus, then I just have minus like I'm gonna have, even if it's positive, I'm subtracting something bigger than it, so I get a negative number. So this minus sign is not to be included. So we're just left with false. And then of course, what's the last step in finding inverse? Switch them around. So maybe I'll write this out. Since inverse of x is equal to the natural log of x plus square root of x squared. So that is such inverse. Okay, a formal definition for you. Okay, similarly, Coach has a definition like this. X squared minus 1. In this case, we don't have to worry. From here, we know we can only plug in positive x values anyway, so that'll work out okay. And then tangent inverse. One half. So this one would probably take a bit of work. 1/2 natural log 1 plus x. Okay. Now, of course, the other three have a definition like this, and if you just for fun, want to figure out what that is, you sure can. It's completely possible to do, but that's up to you. So all these have derivatives, and luckily for you, well, actually, I will probably show one of them at least. I should have left it up there. So I'm going to need. Let's find the derivative of these inverse function, right? So if I want to find the derivative of this, right? Just like we do with the inverse functions, what do you think I should do first? If I want to find the derivative of this guy. Good. So I'll just take the sinh of both sides. And so I get sinh y equals x, which the book doesn't write for some reason. I could have added it, but similar. We still have the same like sinh inverse of x is x, and other way around. Coach has the same thing. I guess in this section it's just not as important to emphasize it, just due to how the inverse of the trig functions work. But anywho, sinh of y equals x. I can take the derivative of this, right? Take the derivative of both sides. What's the derivative of the left side going to be? Not negative, right? Remember, when it comes to these derivatives, we don't have negative numbers on these. Coach y. Yeah. Times what? Awesome. What's the derivative of x? 1. Thank you. Dy over x equals 1 over y. Okay. Again, we don't know coach in terms of x, but we do know sinh. So we'll probably need to remember this identity, right? Let's so I can solve this for coach, right? How do I solve it for coach? We add sinh squared to both sides and take square root, which is going to leave us with coach y is the square root of 1 plus sinh squared y. So I'm going to write that down here. It's going to be 1 over the square root of 1 plus x squared. Good. Now, if you don't remember these ones as much, that's okay. It might be something like if you're working with a problem and you, oh yeah, I happen to remember that, and you can use it. We will use other methods to evaluate these as well that might be more easier to remember, because after a certain point, there are a lot of these derivatives to know. That's why even I do write these, but you know, I have trouble remembering some of them at a point, because we just have easier ways to do it. Okay, so that is the derivative of sinh inverse. Maybe for fun, let's show that our definition, the natural log one, gives the same thing, right? Because we should expect it to, right? Let's see what the derivative of the natural log of x plus the square root of x squared plus 1. How do I take the derivative of this?
First you have
And I multiply by the derivative of the bottom, which is what? Might take a bit to do the derivative of the Awesome. So yeah, so a little bit of chain rule there that we want to work through, but nothing too terrible. So we're going to get 1 over x plus the square root of x squared plus 1 times 1 plus x over the square root of x squared plus 1. And then we can kind of go through and multiply this a bit. I might get a common denominator here. So I'm going to get 1 over x plus the square root of x squared plus 1 times square root of x squared plus 1 plus x over the square root of x squared plus 1. Oh, great. But notice this and this are the same. So we cancel. So either way, you get the same thing. Again, maybe it's just easier to remember that, but you can find it using the natural log definition as well. So good. Let's go ahead and write out the rest of these derivatives for you to have. Just keep them all neatly together. Post inverse is 1 square root. So this one's quite a bit different. It's going to be x squared minus 1, so something to keep in mind, not just negative 1 plus x squared. Derivative of tangent inverse is going to be 1 over 1 minus x squared instead of 1 plus x squared. It's going to be negative 1 over the absolute value of x times the square root of x squared plus 1. Again, I didn't show those formulas, but I'm the derivative of negative 1 over x square root of x squared minus 1. And finally, we have the derivative of inverse is going to be 1. Okay. Now, the most notable thing here is that these and these are the exact same, but actually they're not. They're the same function, but the places where they're defined are different. Okay, so essentially where you're going to have 1 over 1 minus x squared for tangent inverse of x is different than where you're going to have 1 over 1 minus x squared for cosine inverse. And I think it's the same thing for these two, like for something similar to that. There you go. If you wanted, I probably won't throw those options out. There we go. Okay, let's finish up by doing a derivative and by doing an integral. I just noticed over problems. They have ones like that. They're just smart out the formulas. integral sinh code, integral code, and integral secant squared is going to be tangent. Or even actually, I'm going to just pause it here because that would make more sense. The integral negative c, and then the integral c. So if you need those are there. Just so I imagine some of the sections we'll use them. Those work very similar to the trig functions in which we can actually find an integral for them, right? Just pretty easily. We don't have to use any fancy tools at the moment. At least if they're in those forms, right? If I run to like just hyperbolic secant or hyperbolic cosecant by itself, or hyperbolic tangent by itself, we might have a bit of a worry, but we don't need to stress too much about that. So I'll write those out. If you, for some reason, really want like the integral formulas for all of these, which again, it's okay if you don't, but it's just really going, if you have this, then you're going to get that, etc. Okay. And I'll go ahead and add this. Okay, let's do these last examples real quick. So, this is example 2. Problem set this one. We're going to find the derivative of cosh inverse of the natural log of x. Okay. So, what do? Hopefully, it'll be pretty straightforward. Great. Does everyone follow that? Okay. Yeah, it should be right. I'm just doing chain rule. You just plug into the derivative formula. It's going to be good to have this written down. So that's that one. And let's do an integral real fast. We're going to have integral from 0 to 1 of 1 over 4 squared dx. Okay, it's fine. Just keep going. Thank you. Okay. So I have integral from 0 to 1 of 1 over 4 minus x squared dx, right? So which one of these over here does that look like? Yeah, so we'll stick with tan inverse. We don't need to do all the argument about, oh, well, it kind of looks like, cotangent inverse, and you're just getting into, not that necessary stuff. So this looks like tan inverse, so we're going to stick with that. Awesome. So I'm going to try to use that formula, right? So I want to essentially, I'm going to put this into backwards. Okay, but of course, I don't have the exact form I want yet. So what should I do to get it into that form or make it look like that? Factor out of 4, good. So this is going to be 1/4 integral from 0 to 1 of 1 over 1 minus x squared over 4 dx. Again, this should look familiar because it is. We have x over 2 squared here, right? So we're very close. What should u be? Awesome. U be? Yep. Awesome. or I can do dx is 2d as well. So putting that back in, I'm gonna get 2 times 1/4, which is gonna go 1/2. I'll change the bounds, so 0 divided by 2 is 0, 1 divided by 2 is 1/2, and we're gonna have 1 over squared u. What is the integral of 1 over 1 minus u squared? Yeah, so it's just tangent inverse, right? This is why we just, well, let me have these derivatives, by my side, use them. And then this is going to be u, and that's going to be from 1/2, suppose, from 0 to 1/2. Now, we are a bit unfamiliar still with some of these values, right?